All right. Well, Tesla is on the eve, hopefully, we'll see, of releasing version 14 of FSD. And this is something that Elon has talked up quite a bit, that we are going to see a version of full self-driving that feels sentient and is going to achieve significantly better than human level driving performance, anywhere from 2 to 4 times, as much as potentially 10 times, but he's not really willing to commit to that for hardware 4 and version 14. But either way, something that he's expecting to exceed the level of human safety driver performance. And so today I have Phil Beisel with me, and we're going to look at exactly how does Tesla plan to finally crack that upper ceiling and achieve better than human level driving performance with full self-driving. Even though this is still an end-to-end neural network approach, what is it that Tesla is doing differently this time around that allows them to bring Robo Taxi as a product home to market, because they have finally surpassed the minimum threshold that they need to for safety? And so, yeah, thanks for being with me, Phil. And let's dig into why Tesla is able to do this. You wrote a great article here recently on version 14 of FSD. It's part 7 of a series that you have on the magic of Tesla's FSD. And so for anyone who wants to dig deeper into the nuances of this topic, I recommend that you go onto X, find Phil at P Beisel, Pbeisel, and then you can look at his list of articles. It'll be right there for you to reference. So what is the big main difference that Tesla is implementing this time in version 14 that they've never done before, or at least not at this scale, that is allowing them to do this, Phil?
Yeah, there's basically two answers to that: larger model and a big lean in on reinforced learning. So I think both those things are worth discussing. Yeah.
So which one would you like to start with? I think
Well, let's
everyone's
talk.
going to assume, yeah, the big model is going to be a big part of it.
Yeah.
But
I mean, let's talk about that one because it gets a lot of airplay, and it's at least worth it gives us a baseline to build on, I think, in the conversation. I mean, what we have here is it's been stated by Elon, it's been stated by others in the organization that version 14 is a model that's about 10x larger than the version 13 model. And let's break that down a bit. You know, a model is it's an architecture, it's a neural network architecture that is basically a bunch of data values, numeric values that are quantified as what they call the weights and the biases, or the parameters of the network. So weights weights are the connections between these little nodes, neurons in the network, and and biases help filter the data as well. And the combination of those weights and biases are called parameters. So when we talk about a 10x model, we say that it has 10x the number of parameters. Um, and usually we're really talking about the weights here as a measure of this. So why build a bigger model? Well, what we get out of it is we get more nuance and more effectively decision points in the neural network. So if you think about the neural network, it's a driving function. You know, data comes in the form of light through the cameras, photons, if you will. It goes through this function, and the function determines ultimately how to actuate the principal controls of the vehicle: steering, angle, accelerator, brake. Okay, so that's kind of like photons in, controls out, and the middle is the driving function. So we made the function, in this case, much more rich and more, it gives it more uh, effective decision points. That's a big deal. In and of itself, it's a big deal because the bigger model, and by the way, the bigger model more than likely comes with a lot more training data. So they probably pushed a lot more training data through it in the imitation learning side, which we'll talk about. Um, and I think the bigger model itself is a big push because what's important to recognize is that, is while it's desirable to have a much bigger model. Like you might say, well, why not 100 times? Why not 200 times? Why not 1,000 times bigger than the previous model? It largely comes down to what you can run in the inference side on the boards in the car, and what's your number of inference cycles per second. So you've got this kind of happy place where you're saying, I want 30 inference cycles a second on the vehicle. You're able to achieve that maybe in the hardware 4 vehicles with a certain amount of tuning on version 13. Well, you 10x that model, and what was running at 30 times a second is now running at 5 times a second, and you're disappointed. So you've got to now tune that model to run it through at the inference cycles that you hope to achieve. And there's some obviously minimums that they think are necessary. Like you wouldn't be down to 1 a second; it would be too low resolution to make good driving decisions. But you probably don't need 60 a second, or maybe you do. So that's a decision that they make, and you can't just willy nilly build a bigger model. While the training, you might say, well, how much more training time is needed on that model? Okay, maybe let's just let's just say it's linear. Keep it simple. 10x more training time. I mean, I think we're pouring in more data as well so um, you know, I think that the beauty of a bigger model is that I think you can absorb more training scenarios in a sense. So in other words, it can build more nuance. I mean, if you start um, taking a infinite number of training samples and run it through a certain model of a certain size, you start to, as we were saying before, like overfit the model to a certain extent. Like you're not really getting more bang for your buck. But if the model is much, much bigger, now all of a sudden you're getting more bang for your buck when you throw a larger training set through it. So the compute side, obviously, for lack of, to keep it simple, is about, if it's a 10x bigger model, it's about 10x larger compute cycle to train it. But we really worry, and I think Tesla really worries about the inference side of this, what happens on the car. So that's one package of stuff that's going on with version 14. And I think the other probably more significant change to version 14 is that in previous versions, I think we were more focused on the imitation learning. What is that? It means that it's a type of supervised learning where we take training samples from actual drivers and potentially simulated drives, and we run them through the system with discrete known outcomes. And by doing that, we can adjust the model's weights and biases to get the controls to do the right thing, right? To navigate the driving scenario properly. But what's happened here is there's been kind of a move towards reinforcement learning. And
Before we move on to reinforcement learning, can I ask, like, for viewers who aren't as familiar with machine learning, is it fair to say that the way that imitation learning for this scenario would work would be, if you just imagine a 2D graph of maybe all sorts of different driving scenarios, and then you populate that with a bunch of real world data from real world human drivers, and you've curated that data set to be, good drivers, so you don't have bad driver examples in there.
right.
The thing that imitation learning is doing is it's getting the computer to know which one of those examples of real world human drivers you would pick in any given scenario that you would be presented with, to then imitate, like do what Joe did in this scenario,
Yeah.
not what Max did in that other scenario.
Mm-hmm.
And you're just trying to get it better and better at picking the right human to copy, to pretend that you're doing in any given driving scenario that you're presented with.
The goal is, in neural network speak, is to minimize the loss. And the loss in this, there's a functional aspect of a neural network training called the loss function, where you're trying to minimize that down to the smallest amount. And when you've done that in the training cycle, you've reached a happy state. Let's let's do this in an easier way. Let's take handwriting recognition as an example, because it's a simpler, get your arms around it. So imagine that we're just looking at having a neural network determine whether the user wrote the number 0 through 9. So we'll keep it even simpler, just numeric, And what we do is we train it on millions of samples of zeros and ones and twos and threes. And, there's difference in the sevens and the European seven and the how US folks write this. And what we've done is we've labeled this huge set, massive labeling of, a massive set of data. Labeled means that we have literally said before we started the training process that that set of pixels, that set of things in the digital is a 1, and that set is a 2, and that set is a 5. Um, so it's really not magic at this point, right? Now we take this training set and we run it through the training process. And our loss function is a distribution of probabilities that it is this value. So the outcome is it a 0? Is it a 1? Is it a 2? Is it a 3? Is it a 4? Is it a 9? And so let's say that we've got something that's like a 2 and it's a 3, and it may say, well, we're 80% certain it's a 2, but we're 19% certain it's a 3. That's kind of close, although there's 80% certainty, we would probably call it 2, right? The loss function helps us minimize that down to get those certainty factors to the best to match the initial labeled data. Okay. Now, that's sort of somewhat easy to understand, I guess, maybe. When we get into driving, the loss function is more about achieving the proper driving outcome, which is proper navigation without hitting obstacles, et cetera, et cetera. And it too is labeled data. It's labeled differently, but it's labeled data. And to your point, Hans, what Tesla has done in the imitation learning side is they have selected the best driving samples from, we'll call it the best drivers. Uh, I don't think they know it's that Joe is a better driver than Fred, but they do know that the scenarios that they've labeled from Joe, and by the way, labeling isn't 100% manual process. There's a computer process involved here, auto labeling, that these samples from Joe tend to have better outcomes from better fluidity of driver and safety of driving. So when we look at something like FSD and we say, oh, FSD is, this version of FSD is twice as safe as human drivers, really we're talking about that average human driver, right? Because we've got people all over the spectrum. We've got people that are extremely poor drivers, and then we have people that are NASCAR drivers that drive on a Sunday on the road and are pretty good at navigating, potential collisions coming their way, right? So, so by selecting the best data, uh, that is what we do, or that is what is done in this imitation learning. It's imitating the best drivers, and therefore we push it to better than your average human by certain measure, right? Based on the amount of data we have. And remember, we also must have the scenario data. We can't miss driving scenarios and say, well, it's better than it's better, it's 5x time better than a human. Well, what if it's never encountered this type of intersection or that type of intersection or this type of lane change? It needs to encounter uh, most every potential driving scenario. This is why FSD is a very hard problem, because the tail is very long. I say the tail is longer than the creature it's on, right? It's like there's a lot of driving scenarios that you want to capture in your training, because if you don't capture a whole bucket of them, then you're not safer than anything. So, and that's all before we start the reinforcement learning.
Yeah, so let's go ahead and move to that now. So what is reinforcement learning? How is it different from imitation learning? And why is Tesla moving in this direction now for version 14?
Well, in a simple way of stating it is imitation learning allows you to kind of move all the way up to the best drivers, and of course, much better than the average drivers, as we've just kind of said. Um, but reinforcement driving is going to allow us to jump over that because now what we're doing is we are doing a different process, sort of a different process. I mean, ultimately, the neural network architecturally is the same. It has the same number of weights and biases. It uses the same, a similar kind of loss function in the model to set these parameters over these training cycles. But the training is different now. Instead of running training samples through and having this discrete loss function and doing this process that would require a lot of explanation, but it's functionally called backpropagation, where we walk backwards and reset all the value or set new, we nudge these weights and biases to some happy place. Like we move a 1.7 to a 1.73, and that's better, et cetera, et cetera. What we do in the reinforcement learning is we set FSD loose, uh, and we call that an agent, and we set up a scenario. And so let's walk through one. Let's say that we are hyper concerned about pedestrians coming into the roadway unannounced. Like they peer behind a vehicle and they just go up in a roadway. And what are we trying to do? We're trying to avoid hitting them, right? It's like the worst thing possible. Now, in imitation learning, we may have covered a lot of those scenarios. We may have covered a lot of um, pedestrians and intersections. We may have covered a lot of that in simulation, where Tesla has a pretty effective simulator to add pedestrians to an intersection, or change the way they behave. Right? We can take a happy behaving, someone who walks the intersection in a regular fashion, and then make them effectively just turn immediately and go the other way. And so now, instead of having the clearance to go by them, all of a sudden they're coming back into the path. With reinforcement learning, what we would do is we would set up a scenario. We'd say, okay, let's make this pedestrian appear. And what we do is we set up essentially rewards and penalties. And we say, if we hit the pedestrian, we will have a -50 reward, like really bad. But we also want to avoid other things. Like we don't want to brake hard so much in our lane that a car behind us collides into us, because now we could injure ourselves as well as the person in the vehicle behind us. So maybe there's a reward associated with that, like -25. So not as, it's worse for the car to hit the pedestrian coming into the intersection than getting rear-ended. And then we might say, well, we also have a bunch of laws to contend with. Like we shouldn't just change lanes um, without signaling or aggressively. But in certain scenarios, it's better to change the lane, to jerk into the other lane than to hit the pedestrian. I mean, well, in every scenario, it's better. Um, but we have this possibility of colliding with a car in the adjacent lane, right? But if we collided with the car in the adjacent lane and we're both going the same direction, we're both going 60 miles an hour, then that collision is a very minor collision versus killing a pedestrian, right? So we may say, well, there's a negative -5 associated with with jamming into that lane quickly. And so now what we do is we allow the system to run a large number of what would be called trajectories. And I think from vehicle, it makes a lot of sense. Trajectories like run this way, do this. And then we go through this and we score these. And by doing this, we can now have a slightly modified or a different kind of loss function that allows us to also back propagate through the network and change the weights and biases. But what we're doing in reinforcement learning is we're essentially setting up scenarios that are unique, potentially unique, that we may not have real world driving data for. We certainly don't have real world driving data for hitting pedestrians at scale. And we wouldn't want to have that kind of natural data in the system, right? Because that would be like happening. Um, and remember, in reinforcement learning, it's all running through a simulated inference, right? Which is really kind of cool if you think about it. Like, what that means is that Tesla has a real world physics simulator that can effectively fake out, if you will, the inference side, the compute side of FSD to make it
Yeah,
think.
like a real AI for board or a virtual AI for board
Yes,
running in
exactly.
emulation. Yeah, that
Yeah, it
it
doesn't.
thinks that it's really driving, but it's not. It's just all
It's all virtual,
happening. Yeah.
and and then therefore by having a great real world physics simulator, you can really lean in on this reinforcement learning. And so you mean what you need in reinforcement learning is you need great simulation. You need obviously um, a
Hopefully
plan.
low cost and fast. Great simulation.
You need, yes, right. In other words, great simulation isn't just um, physics perfect simulation. It's also has to be generative in real time. And it means that, yes, so you need so low the cost of compute to build the outcome. Like I'm sure that 5 years ago that they had something pretty good, but I bet 5 years ago it used too much compute to make it practical.
Yeah, if it takes you 10 minutes to generate one frame worth of simulation
Yeah,
and you need
it's
to do
not.
30 frames per second,
Yeah,
like you're just never going to be able to do enough simulation to
right,
actually provide the
right.
amount of data that you need to do RL effectively.
Yeah, so in reinforcement learning RL, as you said, um, you are running hundreds or thousands of scenarios in parallel, whereas you have not captured that in natural data, natural driving data. Like you have not, okay, a car goes by an intersection, and uh, pedestrian walks out behind a car prior to the intersection. Ooh, that's the one you really want. But how many do you have? You have one. You have one of those, and you don't, and the car has a fixed trajectory that it had selected and was captured in the training data, right? So you really don't have much. Now you could take that and you could put it in the simulator and you could build a couple scenarios for that. And you could say, okay, that's cool. Now we've got the real world captured data. We've used that as a template to create some variants. So now we've got 10 variants of that. But what if we want to do 1,000 variants? In a sense, that's what reinforcement learning is doing. It's like, oh, let's just really change up the scenario to not only do great simulation, but now to be able to use that simulation at scale. Um, and the interesting thing about it is that's one of the reasons I think we're at that door, because now we're starting to get to the point where we have a lot more compute to be able to apply to the problem. So I think like I don't think a lot of people would say, "Oh, this was a bad idea of 2 years ago." I think it was more a fact of like, well,
You didn't have the compute budget and the energy budget and the data
exactly.
pipeline to be able to support doing this at this scale yet.
Yeah, I mean, they probably could say, "Let's do 5 scenarios." Okay, great. Boy, we would really like, engineering team, we'd really like to do a couple thousand of these. Well, what do you need for that? Well, we need, 100,000 GPUs and half a city's worth of energy um, to be able to do these things. And remember, every one of these reinforcement learning scenarios are kind of like unique little flowers, right? Like, in other words, they're scenarios that you don't necessarily you're trying to build scenarios that are unique in field and you're like, oh, okay, this would be really great if we could do a whole bunch of scenarios to avoid erratic or suddenly appearing pedestrians, example. Or let's do a whole set of scenarios that lead to smooth lane changing. Uh, or uh, here's another one that's probably clear to a lot of people when they're in FSD is, you know, you, the vehicle needs to take an exit. Cars are lining up. When does FSD cut in? You know, like, does it wait to the end and cut in, which is, socially awkward? Does it sit in the back of the line, like the most foolish person, in the scenario, or does it find its
Happy
happy
medium.
place,
Yep.
wait for that, semi not to be able to catch up and sneak in that causes nobody any anxiety. And so that's something that you could like really, really run up in a whole set of reinforcement learning scenarios to get that thing tuned really well. So, I mean, we've got a box of things that some of them are safety related, and that's what everybody thinks about when they think about a car driving itself. They worry about the safety aspects, but really, to make it feel good to the passenger, and to use Elon's word sentient, meaning like, what does that mean? It means to feel like a human, a good human is driving you. You have a good chauffeur driving you, or effectively you're in control of the car because everybody thinks they're the great driver. Um, in the isn't that true? Um, in those scenarios, that's what we're trying to achieve here. We're trying to achieve that with essentially, I think a good way of thinking about reinforcement learning is just much more variance from what we could have captured on the imitation side. And now that we have the capability of doing it, we're going to do it so that we can kind of codify all these amazing variances in both safety and driving fluidity, right? Clean driving, like sentient, meaning like it behaves like a human, or actually, from
Better
anybody's
than,
perspective, a
yeah.
good human driver as opposed to, a bad Uber driver or something.
Yep. And I think one of the things that's important for people to appreciate is that, if you want to like take one real world driving scenario and you want to multiply it, and you say, okay, let's change the way that this scenario presents itself in 10 different ways. And then for each of those 10 different ways, let's run 100 different trajectories
Right.
to pick
Exactly.
the best one. Well, then you have, 10 scenarios times 100 trajectories per scenario is 1,000 new data points that you're generating from one real world piece of data. Now, hopefully you're pruning those down, and that's not all going back into your training set, but
Right.
it
Right.
takes a lot. Like, it's very computationally expensive to explore those 1,000 different
Yeah.
scenarios in order to then say, hey, we want these 10 or 20 new pieces of data that we're going to now feed into the training set for the next version of the model. And yeah, that's why this is so computationally expensive.
Yeah. I mean, if you think about it, it's the difference between gathering field data, storing it as your training set. Like, in other words, if you store a set of, you gather data, you process it. The processing portion is to label or auto label the data to the outcome that you're trying to achieve, just like the handwriting recognition problem. And once you've done that, it gets stored somewhere, right? So in theory, if you train a version 13 model and you said, okay, we've built these batches of data, we've done these number of epochs, the kind of cycles through the training, and if we know what our input was, uh, it's in storage somewhere, sitting, somewhere in storage, and we bring it to bear, we should be able to build exactly value by value the same exact model. With a little bit of asterisk, exactly. But anyway, um, reinforcement learning allows us to basically really kind of think of it as more runtime training. We're really now we're in a circumstance where we can say, okay, we know we would keep, if you will, from a storage perspective, the original generative piece, the trajectories we used. Obviously, we need to kind of have all that as you might call it source data, but now we can run these things that they're generatively happening for the simulator in real time. Uh, and so now we've taken what might have we may have used the simulator a lot in imitation learning, but it's more about taking training sample A and creating A prime and A and B, B and C and D, and then putting them in a storage box and saying, okay, that's our training data. Here we're saying, okay, let's take A, let's set up a scenario and we'll run it through, 1,000 different potential randomized trajectories. Like we can literally have the car literally come from like say it's a entry point of where the vehicle is, and the two-lane scenario could be very dramatically. The speed can be varied, and even to the point of randomness, right? Like enters the driving sample at 62 miles an hour. Okay, 59, 32, 17. Um, is in a mode of accelerating, is in a mode of braking before encountering any of the um, potential rewards or penalties within the sample set. So you can just have this like incredible variance, and you're really pretending or running through billions of inference cycles to train your neural network. And that's it's the right way to ultimately, I think, do it.
What is the reason that you feel confident that, like, I guess stepping back, it seems like RL is becoming a much more popular and common way to continue to advance the frontier of AI these days in a number of fields. Um, why is that something that's happening now, not just with FSD, but in other areas?
Mhm.
And why are we so confident that this is what Tesla's actually doing right now?
Well, I mean, Elon mentioned it in the All In podcast that this was happening with V14. Pretty much said it out loud. So and certainly I've been thinking about it for quite some time, seeing kind of reading the various tea leaves of engineers. Again, I don't have specialized knowledge. I don't work at Tesla, and I don't know their secrets. But I kind of, based on my engineering background, I can read the room and try to understand what I think they'll lean in and where they're going. I think one of the reasons that we are seeing a lot more reinforcement learning versus just pure imitation learning is because we're starting to get good scale out on the training side. We're starting to, we've got. I mean, I think in some sense, the way to think about this in the kind of most simple minded way is, gee, if we could just run more potential scenarios through the system, we'd have a better system. Well, this is giving you the opportunity to do this now with a certain technique. Don't get me wrong. It's not just imitation learning at some scale. There is a certain technique involved in how reinforcement learning works, but but ultimately, what is it doing? It's doing the same thing at the finish line. It's doing exactly the same thing. It's adjusting the weights and biases. It's nudging them into it's taking the driving function and tuning it, right? It's tuning it up. And I think what we've realized with any of these things is that the real world data is incredibly important. Okay, it's extremely important. I don't think you would, especially in driving, it seems inconsistent to want to start with just simulated driving data. That's like, I mean, imagine if you did that with handwriting recognition and you said, let the computer just simulate a million different digits written by humans, Um, would you miss a lot? You would miss a lot. Would you miss less than the driving problem? Yes, a lot. But um, but ultimately, uh, what Tesla's doing is it's like the really the perfect balance. Starts with an immense data stream from real world driving data, has curated that over time to the best stuff. Like, like we know our vehicles. Look, if every vehicle recorded all of its driving and sent it to Tesla, uh, that would be, well, that's an impossible thing. That would be like petabytes an hour or something. I don't know, making up numbers here, but it would be overwhelming. So now we need the evolution of the thing is you have a small set of vehicles that could record all data, and then Tesla gets smart, meaning the engineering team says, okay, now in either shadow mode or in driving mode, we want to cherry pick data sets that are interesting and bring them back to the data center effectively for potential training data. Then on top of that, oh, let's go build this simulator that allows us to use those data samples as effectively templates, like perception templates, like what's in the driving scene, and then create variants in that. And then we could use that. Oh, okay, good. Let's just go label a bunch of those original samples and then these new samples, and we'll create essentially a box of training data. And now with this reinforcement learning, we can say, well, now let's really blow this up to the next level where we can use the simulator at scale to allow vehicles to run down trajectories that they couldn't possibly have seen in natural data. And I think that's kind of the door we're at. And I think that's why, in a sense, to get much, much better than a human, you have to move beyond the human's data, right? That's really kind of the obvious thing. Like, even if you say, well, here's the average human, and to be 10x better than the average human, you could probably reach that line with imitation learning. But if you want to get 20 times or 30 times or really go beyond that, you've got to apply some new technique, and it can't just be take human data and you know label it better outcome. It has to be a lot more data in the system. So it's just it's really fascinating. I think we've really gotten to the point where um, we've learned that. What have we learned over this whole process of AI? When we all came into this, it just kind of it's hit us. What do we learn? We learned that uh, if we can apply unlimited compute or a lot of compute, that we can get really good outcomes. That's like the effective reality of the bitter lesson, right? If you for viewers, that's a particular paper. I forgot the author's name that basically said we can, instead of developing extreme amount of technique that potentially mimics human cognitive processes, it might be better to just run it to ground through scenarios, et cetera, by applying compute. And so now that we've gotten to a happy place where, while compute isn't by any measure free, companies like Tesla, and in particular Tesla, have learned to build these beautiful, coherent training clusters at some scale and have put enough money into the input to bring energy to bear, because to run these things it's funny how we start literally quoting data centers now, not as compute nodes, but rather just based on energy. It's really fascinating, right? I mean, we don't that's kind of how the vocabulary, or how the way the descriptive language is changing. Let's go build a 10 megawatt this. Let's apply 10 megawatt to this, as opposed to just saying we're going to have 100,000 GPUs, et cetera. So I think that's kind of it. It's like people have learned from the bitter lesson. they're applying the bitter lesson at scale, and things in the, just from a technology point of view, have kind of coalesced to allow that behavior, that model to work. Um, and that, I think, is what we're starting to see the fruits of that come to us. You know.
Yeah, and that's where I wanted to go ahead and put this on the stage here for us to look at that. This is something that Elon has also applied at XAI, and this is a chart of the compute growth at XAI for their Grok training. And so, it shows the amount of training that they do of just pre-training the model for Grok 2, and then they did 10x that to get to Grok 3. And then when they did Grok 3 reasoning, they did the same amount of, pre-training for Grok 3, and they added just this little bit of RL on top of it to guide the reasoning process. And then the Grok 4 reasoning model has the same level of pre-training as Grok 3, but then they just 10x'd the amount of RL that they did on top of it. And that's what produced this model that was so much smarter. And then they haven't really told us what they did for Grok 4 Fast, that they were able to achieve almost as good of overall performance, much faster, 47 times less cost. And that's pretty incredible. But this does show, the power of what Elon is already doing with RL over at XAI. And I'm sure the lessons that he's learning there are things that he's applying at Tesla. And I just wanted to get your commentary on, if we can make a Grok 4 Fast in the land of LLMs that can achieve like 90% of the performance of Grok 4 Pure, 47 times more cost efficiently and way faster. Like, what does that say about the future of what superhuman driving models can be then distilled from these big models that we're making, and then hopefully made compatible? Like, can we make something like that compatible with hardware 4 in the future, or hardware 3?
I don't know how to run this out metaphorically the same way. I don't. Like, I just don't know. Like, haven't spent too much time on how they did the fast model. I don't know how it. What I'm saying is, I don't know architecturally how transferable the techniques are. I think that the question a lot of us might ask is, how special is FSD if we get to some level of, if a human can drive a car and a human's a general compute object, in other words, it can see any real world scenario, and that might be called, um, we have a general intelligence model and we reach some artificial intelligence. I mean, in other words, if you installed artificial general intelligence in Optimus, can you throw Optimus in a Ford Focus and have it drive anywhere it wants to?
Yep.
Right. I mean, that's one way of thinking about it. Then you would say to yourself, okay, well, if that's true, then if somebody else builds a comparable humanoid that can sit in a vehicle in its natural state and control the vehicle much like a human, could it do that at scale? And I really don't know the answers to that. What I think is that the truth of the matter is, I mean, at some level of infinity, the answer is of course yes. But the problem is that there's a lot of ground to cover between a simple yes and reality. There's a lot of ground between that. And what Tesla has done is by, like in other words, if you hit me with the task of, you said, okay, I want you to go build a autonomous driving system, and you said, how are you going to approach this? I want real world data as my baseline data. I don't think I would do without it. Okay. And then I would be challenged by, well, how do I contain that data to the best data? How do I find the best data with the best outcomes?
And make it representative of the actual real world.
Yeah, I mean, if I just, yeah. So, for example, if I just lean in on simulation, I don't know what I don't know. I don't know the scenarios that I'll encounter in real world that I mean, there's no map. There's no like, big box where you say, well, I've checked off all the potential driving scenarios. It's near infinite. And um, a good way to think of it is you're always sort of asymptotically, you're approaching some goodness of completeness by the more samples that you take in from, say, in this case, fleet data. So if you assume that there's about 5 million vehicles, Tesla vehicles potentially contributing data to the training corpus, to the labeled set, then you would say, okay, the more they drive, the more data you collect. Over time, you're approaching the line where you've got, you're narrowing the tail, you're chopping the tail off, you're getting to some point. But what you don't know is exactly how long that tail really is. And I think that's one of the problems with this particular task is maybe somebody could tell me I'm wrong and there's some computational way to know that you're reaching 99% of all scenarios in driving. I don't know how you do that. I might just not know, but I don't think you can do that. So then if that's true, then you can't really do it in pure simulation, because that's really where you've actually, by simulation, you're not really saying go build random simulation. I mean, you could, but you're probably saying run simulation with these varied scenarios. So at the end of the day, what you probably want to do is start with real world data and be in a position to augment that data to more scenarios, hence like reinforcement learning, or just more varied base scenarios. Like, um, oh, wow, we can bring in um, these intersections and we can now, well, we can bring these in and we can add blinding snowstorm to every single one. Okay. But would we do that to the entire selectable? Yeah. If there was infinite compute and infinite time to do the infinite compute resources and compute was, zero time, then we might say, well, let's simulate potentially everything. But we don't know. Like, so we don't have the luxury of that. That's not a luxury, right? There's finite resource, finite energy, finite compute resources. So we have to use like somebody would say, well, how long does it take you to, like, let's just strip away all this crazy stuff we talked about. And we said, okay, how long does it take to train version 13 of FSD? And the answer is probably somewhere between 2 to 3 months, um, running effectively flat out in the data center. Don't know if it's 2 months. I don't know if it's three, and I don't know if it's four, but it's not 1 week and it's not 3 days. And it's also not 10 years because there's just practicalities to what you need to select yourself into a place of approachable engineering reality, right? You have to say, well, I can afford money wise and time wise this much on my training side. Um, Obviously, I'll build a bigger cluster and I can do more training in parallel. Okay, but that doesn't require less energy, right? It requires actually more, and in fact, it requires more focused energy at a given place. So, which is a harder problem, right? It's not distributed. You have to focus the energy in a it's like powering a certain city. So, I think there's these engineering practicalities. This is why none of this was possible before we had GPUs, because we couldn't do this in CPUs and we can't do this in emulation mode in software. We have to do this at the silicon level and with great parallelism, the GPU level. And only till we got to that happy place were we able to really decide that, in effect, you might say the neural net was sitting there waiting to be populated by numbers. Uh, but that didn't happen until we had a way to do that within practical scale. So it's easy to do a small little teeny model, and you could almost do it on your MacBook at home. But I mean, if you took a MacBook and you said, let's take the training data that to do version 13 required and just do it on your MacBook, it might take 2 or 3 million years. I don't know, some number, some crazy number. So, there's these practical things that you do in engineering. It's like, what's the practical limits? Like, what are you willing to spend from a dollar point of view, from a time point of view? Um, but obviously you've got to achieve your objective as well, right? I mean, you can't underspend and not get to something that drives itself. But now we're in this place where, well, we'll never have, I mean, those software people eat all the hardware there is, right? So, so no matter how much hardware there is, software people like myself will eat that hardware down to nothing. And sometimes we do it because we're just flush with hardware and we are super inefficient, and those are terrible engineers. And other times we do it because it's available and we want to use it. And so there is this happy place, right? It's completely um of what we can achieve given the resources we have. And obviously we're going to demand more. I'm going to say, if only we had, if Elon says, well, how do I get up to, I'm at 2x human safety, how do I get to 10? Well, I need a larger, um, I need a larger data center, and because I need to run more examples, whether you from an imitation or reinforcement learning side, I need to run more scenarios. Oh, I want to capture more data also. Well, what does that require? Well, that's not free, right? I mean, that's like, what's interesting, I was always thinking is like, how many people have, when we think about, training FSD, we really just think about taking these training examples as if they're just sitting there in the air and running them through. Well, they're sitting on a large storage cluster. That costs us a lot of money. Like, it takes, there is a massive storage block sitting at alongside uh, the training side, holding all of this data, um, and labeling it appropriately, and keeping it in a happy place, so that we can actually bring it through the compute cycle on a training run, right? So yeah, I think what I'm trying to say in maybe too many words is, all engineering problems are resource constrained, and you have to determine what's can you reach solution with the engineering resources, or with these resources available to you. Um, if you can't, can you get more, or can you change technique? And I think what we learned with the bitter lesson is, it isn't worth changing technique. It's better just to brute force it, because we've reached that place where there's enough of it available that we can brute force the rundown of the tree.
Mhm.
Right.
Thank you, Jensen. Yeah.
Yeah.
And I think
And he's
you asked
happy to
earlier.
and he's very happy to give you that.
Yes.
Yeah.
Yep. Yeah. The more you buy, the more you save.
Yeah. Yeah. Of course.
So, yep.
Yeah.
I think Rich Sutton was the author
That's
of the
right.
bitter lesson.
Yeah.
And yeah, it is stunning that that paper, didn't emerge until 2019, well after Jensen had started to just deliver consistently on rapid growth of, parallel processing capacity.
Well, I mean, I think the funny thing about that, Hans, is that I think, from a pure AI research, I mean, we it's funny how we all like it. AI is a pretty, you go back in 50 years or so, AI is a pretty big field of potential different things that were, some of them were run to ground and disposed of. Some still have techniques, still have potential, but we've kind of boxed it all the way down to this thing called a neural network. And, it's, and that thing called a neural network, it's really like, it's not well, there's sort of an architectural framework for that. I mean, if you look at, when when people say, well, oh, I see, it's just a neural network. And if I just had the same um, FSD data, if I just had all that source data, if I could just get all that data, I could just build a neural network. Good luck with that. I mean, there is an extreme amount of technique. If you read one of my, I think it's paper 5 or article 5, I talk a lot about mixture of experts model, right? This is a technique that minus all of what we said about imitation and reinforcement, we talk about what is the actual interior architecture of Tesla's FSD solution. Well, there is a block of perception. There's a block of planning. The perception is to see the environment. Planning is to determine what to do. And then within that, there are these sub blocks of experts that, well, we don't need to apply the highway driving expert when we're going through an intersection. We just apply the intersection expert. And well, that narrows inference compute massively, right? We basically take parts of the neural network and they go dark for that period of where we are. But so what I'm saying is there is a lot in the actual details of the architectural model that Tesla has. That is their secret sauce. And they are not telling us what is in that architectural model. We are reading around the edges to kind of like tease it out and reverse engineer it. But that isn't to say that, well, if you just gave somebody the training data corpus and you gave them Cortex and you gave them 5 months that they could produce FSD. I think that would be completely an incorrect conclusion, because it's like, well, you just gave them two parts of the three. You gave them data, in other words, the fleet data. You gave them the compute, but you didn't give them the technique. And the technique is really, what are we doing today? We're talking about, we think that reinforcement learning has become a huge thing in not necessarily starting with, but manifested largely in version 14. In other words, we start with the imitation learning to build us our base model, and then we tune it with this reinforcement learning. And we think that is what they're doing, but that still doesn't describe the interior architecture of the neural network, which I argue is a mixture of experts model. And even with that, we don't know how they align them, how they put weights on them, how they select them. There's like a billion details that we don't know, and we can't just snap our fingers and say it's obvious. It's not obvious. And by the way, it wasn't obvious to Tesla. Tesla has been at this game for, a good decade and run the ground or run into brick walls many times, right? I mean, we know like the great departure in version 12, where they went end-to-end neural network. They tossed, is this what that means to people listening here, is that before that, they were the artificial intelligence, the neural network was used for the perception side, but it wasn't used for the planning side. The planning side was a piece of code, make decisions based on, logical, written by humans, a piece of code. And they went down that path with version 10 and 11, and it yielded promising but poor results, right? Non-converging results. In other words, it wasn't, there's some point where
success was not in the set of possible outcomes.
It might have been in the set of possible outcomes, but not in the achievable ones. So they tossed that overboard and went end to end. And by the way, a lot of their competitors haven't tossed that overboard. Waymo's still got kind of an algorithmic approach to the planning side. I mean, there's technique that they've developed. It's not simple and it's not simple and wrong. It's just that Tesla ran that to ground and said, this isn't going to work. We don't think this is going to work. Let's go end-to-end neural network. And then this is where we find ourselves today. So now, really, in a sense, what they've done is they've discovered the architecture. They built a lot on, you know, building the data pipelines for achieving the training side of that on imitation and reinforcement learning. They spent God knows how much resource on physics real simulation. Huge, huge, like I don't know, I'll say make something up and say 25-person team focused on doing just that. Um, and then they've gotten to a place where now they see an achievable success uh, based on a vision-based system, which they've selected. I mean, we didn't even talk like the early days of LiDAR and why they got dumped that. And now they're like, okay, now for us it's a scale out problem. We think we can achieve it. Version 14 largely does, in my opinion, achieve it. I mean, we haven't seen it, but all signs point to this being the one.
Yep. And I think for readers who are or viewers who are interested in reading more about that decision to go end to end in the inference side of the FSD system, you can go look it up in the Walter Isaacson biography. They go into detail there about how
Yeah.
I believe there was an engineer named Deval Shroff who was also one of the ones who was going back and forth to Twitter at the time, who originated that effort inside of Tesla. And I think if I remember correctly, it had already been tried several years prior and had run into those brick walls that you mentioned. And so he was just the first one to resurrect it at a point in time where the tech stack was mature enough that it could actually work.
I think that when you think about, I mean, a lot of what I think the value I think I bring to this conversation is not that I'm deep into AI, but I'm deep into the engineering process. And I know what that feels like through several things I've done in my career. And what I'd say is that there is sort of this antiseptic outside view of how this works, that there's this thing called R&D, and we do a bunch of R and then we do a bunch of D. But that's not how it works at all. In a dynamic organization solving a problem that's never been solved before, there is lines of research that are run to ground through development. Some of those things um, run into brick walls. It's even more interesting when you start adding organizational dynamics on top of it. Because, for example, let's say that someone told you that you needed LiDAR in the system. And so you went off and you hired, two or three people that are considered the world's experts in LiDAR, whatever that actually means. And they come in and they say, okay, well, in order to do um, a sensor fusion model where we're going to use LiDAR, we need this team of people. We're going to hire this team of people. And once that team starts to find itself into some reality, they don't, they believe in their self-preservation. I mean, just like we all do. So it's very unusual for the head of the LiDAR team to walk into, the overall senior VP's office and say, I don't think I'm needed here. You know, so what that leads to in my mind is that in order to really, I mean, to make really good progress on these types of unknowns, you need to make fast decisions with a decision maker. I mean, this is a key element here, is that, in other words, that's why these organizations, this is why the Musk organizations are so valuable, because he's the key decision maker. And, he has a certain amount of data, but he makes a decision and he moves forward. And internally, we can tell that the best organization is to have a lot of smart people working on the unified problem as versus broken out into these little sub teams and bureaucracies that try to, preserve their own existence, et cetera, et cetera. So it's a messy process, but it requires, I think, a couple key things. It requires a lot of hard work, move fast. In other words, move to failure fast is a very, very important principle here. Is like, if you think LiDAR isn't going to work for you, go prove it. Prove it quickly, throw it overboard, and move on. And I think this is one of the things that Elon brings to his organizations, and in this case, Tesla, is that, you know, um, he's really, really focused on the fail fast model. Like, in other words, we know we're going to fail. The key to be competitive is to fail fast. Like, we have to try things. If they don't work, we reset, we regroup. We don't, with good leadership, we don't end up with this organizational inertia that creates a life of its own that is meaningless, right? Because if the LiDAR organization, you could have a whole bunch of people in the LiDAR organization that know damn well that they don't think they're adding any value to the solution, but they're just going to keep adding it in there because that's why they were hired and that's how they get their paycheck and that's how they, pay their mortgage. So,
Yep. Or Dojo TSMC or Dojo version 3 people who are trying to cook something up to be fabbed at TSMC instead of at Samsung. You're like, Elon realizes, hey, this is an evolutionary dead end. Okay, bye. We're
yeah,
moving on.
and it's really tough. You have to have a really special mind, I think, to not get into the sunk cost problem where you say, well, because I made this investment, I must continue this investment. Um, I mean, the best course of action. I mean, it's better to be smart and a generalist in an Elon organization than an expert in an Elon organization. Because if you have a bunch of people that in Dojo that are relic, for example, why did Dojo fail? Dojo failed because, well, it didn't reach escape velocity quick enough, right? It didn't get to a good production state before the world changed underneath it, right? And I think we can see what's happening here. It's like take the whole conversation we just had here about reinforcement learning. What we probably didn't say enough of in this conversation, although we probably said a lot, was that this requires an enormous amount of inference compute within training cycle, right? So in other words, we're suddenly doing inference in training, not just on the ground in runtime. And what does it tell us? It tells us that, well, a lot of that stuff we've done in Dojo to create the perfect training computer
For imitation learning specifically.
for all imitation learning, like high precision math, um, bandwidth over latency optimization, all those things, they're not useless, but they're not the same utility value as the world kind of changed. So I think that's, like, to be frank with you, I think that's one of the things that they're looking at really hard right now with AI 5 and then AI 6 leaning in on that is what are we doing with these chips? Do we want them? Um, how general purpose do we want them? How specific do we need them? Um, and those are real trade-offs because if we get like functions on those chips that are highly optimized for, say, inference in the vehicle, and we cut out, like we move from a software implementation right onto into silicon on the chip, we may save, or give back. Another way of thinking of it is like we may increase our inference cycle from uh, 15 cycles a second to 45 cycles a second or something like that, which is, maybe our target. But at the same time, we have to look at that silicon. We have to say, well, did we really want to build that core into the silicon? It's going to, the die is going to increase. There's going to be, there's cost to do that. is the cost to benefit there for us to want to do that? And there is a point where you just have to put the stake in the ground and stop, because these processes, I mean, like, people always ask, well, if hardware 4 can run version 14, why do we need an AI 5? Well, that's like kind of a ridiculous thing to ask. I mean, because clearly more functions going to come on to that chip. Grok is going to happen concurrent with inference and FSD inference. So all of a sudden, the chip is going to be doing a lot more. It's not going to be doing just the same thing. It's going to have more function on it. But I mean, we do have to, in any engineering process, we have to put a stake in the ground and say, let's cut, and this is what we've got. You know, and that's a lot harder in hardware than it is in software, because the lead times are much longer. I mean, software is very malleable, and but but it's not free. I mean, like, if you consider, um, like, you go back a couple years and you say, well, there was this algorithmic approach to the planning side, and we say, well, let's go and change this in software. Let's not, you know, we need one more sprint cycle to get these 5 more things done, you know. But what if all of a sudden now your software is dependent on your hardware? I mean, what I mean by that is your software is directly dependent on the size of Cortex. Like, your software is not code written anymore. It's a function that's built out of this training side.
Yeah.
So
Yeah, it's
it's
literally token generated.
yeah. And so, like, imagine that you say, hey, we need another in our block architecture inside this neural network. We need another expert to we have these functional experts for, like, intersections and highways and this and that and so forth. Now we've got a snow one and a weather one and a, whatever. And oh, we need another one. We need some other kind of thing. Um Now we have to train that, and it's it's maybe it's computable, the time it's going to take to train it, but we have to say, oh, that might cost us another, making this up, 3 weeks of training. And everyone's wondering, well, where's that release that was supposed to show up on September 30th? Well, it's the team has made a decision. I think that's what we have right now, is where everybody is waiting on version 14, and Elon's talked about version 14. And I think there's this weird thing, Hans, that happens, is like, well, he's lying about it. Well, that's not how the world works. That's not what's going on here. What's going on here is there is a version 14. Uh, it is a candidate release of version 14. It has a set of things that they decided were uh, the theoretical finish line. And then they did an engineering review meeting with Elon, or internally, and decided that they need 3 more things or 5 more things, or they need to fine tune this better, or add 12 more reinforcement learning scenarios to the mix, or they have to collect more source data because they're seeing real world examples of problems in Robo Taxi in Austin on the ground, where uh, it doesn't center itself in lanes properly. Okay, so now what? And they've got to run all these things. So imagine that you've got a dynamic system, which is Robotaxi in the field, and you're trying to collect data off of that system to improve this other thing over here, which is your next release. And if you insulate it too much from the engineering team that's building this release, then you get no value out of what's happened there. Like, it's it's data, but it's not being processed right. If you jam it too closely to this process, your typical engineer who's looking for uh, more of a perfection in his build is going to suggest to his management, I need more time. And at some point, Elon enters the room. And when he enters the room, he's got 2 thoughts in his brain. Thought one is, I want this done tomorrow. And thought two is, I want this done right. And those things are are somewhat in conflict with each other, right? They're not, you can't like say that they're completely separable things. In fact, that there's trade-offs. And so now suddenly it's him that has to make that decision. He collects data from the engineers. Oh, we want one more of this. We want 10 more of that. And they're probably overly cautious because that's kind of how it works. And he's not overly aggressive because he's got another set of constraints, which is he can't, he doesn't want to deal with a system that, is less, that causes an accident in the field, right? He doesn't, that's, it's worse for him than it is for a bunch of engineers under him. So, you know, this is just a set of trade-offs, and he's got to make the call of, okay, it's good enough. Let's call this version 14. This candidate, let's call it version 14. Let's push it out. No, let's test it for a bit more time. No, let's do another candidate release, and then the things that you or it's good enough, and we'll put those new things in 1401 or something like that. Um, that stuff's happening all the time. So I don't think that Elon shows up and he's, I'm sure Elon was at the point where he felt very good about, let's say, a September release. And then all of a sudden you saw him move the goalpost a little bit. Um, I think it's just because there's more data now available to him and he wants to make a better decision. Um, yeah.
Yep. I think a good example of that for people that's concrete is when they pushed back the Robo Taxi launch event, um, so that they could include the Robovan in it. It's like, hey, if we, give ourselves another 30 days or whatever it was, because I think it was first supposed to happen in September, and then they decided to do it.
Oh, that's right. Yeah.
Yeah, it was going to be, was it 7/7, and then they decided, hey, we're going to do it 10/10 or something like that, whatever it
Yeah, I
was.
think so. I think so. Something like that. Yeah.
Yeah,
Yeah.
and yeah, like the whole point of moving it was like, hey, if we have this extra time, that'll give us enough runway to complete the Robovan prototype, be able to actually show it on stage there, that event. And, that wasn't part of the plan when they announced the original, we'll just say it was 7/7 date.
Yeah.
And,
Yeah.
or maybe it was 8/8, whatever. And then, hey, we're going to add that. We think it's worth it to have that there to delay by, some number of days.
Yeah. I mean, it's, I spent the people watching this probably know somewhat. I spent years, 6+ years at Rivian developing from, the early days of the, the technology all the way to the finish line. And, in the early days, it's sort of easy, there is no obvious, you just hear management say something like in 1 year, you sit there and you go, that's crazy. I can't do anything like that in 1 year. Or, but nobody knows. There's no, there's no perfect system that tells you how many people you need, how many problems you'll encounter. And then all of a sudden there's, a list of things in sort of like your attributes. So in vehicle engineering, you might call them attributes, like things that you desire. Some of those attributes are in conflict with other attributes. And what's crazy is that, like, I'll give you an example where you can blow a timeline up so bad without good leadership is at Rivian we had this problem, and it was one of the attributes is that we wanted cellular. These cars have cellular connections, and we wanted basically a cellular range of like 20 miles of connectivity, right? Because I mean, in vehicles, they come in and out of cell towers, and you want your best, you know, RF signal. And then in conflict with well, at first there was, well, do we want the traditional supply chain version of the shark fin antenna that you see on every vehicle? And you'll see that that's on Rivian vehicles. Well, teams tried for months to bury the antenna structure in the roof structure without materially changing the design of the vehicle to get the proper, everybody's attribute, like no shark fin antenna. Um, Now, going into this, there isn't a certain person there without, I mean, obviously people come to bear with experience and know that it's not, um, until it's tested, it's not known. But oh, okay, the roof material is going to be this, and that's going to create this kind of RF insulation, and we can't get the gain we want out of that. So, oh, and then okay, let's go back to the design team. Oh, no, sorry, they're fixed. They don't want to change the design. Sorry, it's a glass roof that runs up here, so we have no place to hide the antenna structure further back. It's got to be all up front. Oh, we can't do that because we have to have better kind of a better structural thing for crash for safety reasons. So we can't just evaporate that piece of metal that's sit there that create. And nobody wants the silly shark fin, right? Nobody wants that antenna structure. And there's a reason that it was built as an external thing because it's easy, effectively an easier way to achieve your different RF um, signals on the vehicle. And so, how much time? Answer the question: how much time do you spend trying to run that to ground? And no team wants to fail at their mission. If their mission is to bury the antenna in the roof structure, they want to succeed at that. They're going to be trying things, and they're going to be, trying to convince the design team to move design after the design team is like, "Hey, we're done." We're and it's not just done. I mean, it's not like, "Oh, we can move design," but then we've got to go figure out, like in the case of a Tesla, we're going to have to change our what do you call it, the gigacast, the cast for the. So there's these things like they don't these decisions don't magically make themselves. They sometimes you go, okay, I can't. You don't want to say I can't do this, but you may ultimately like recommend to your management. I don't think we should do it in this version. It's the best escape patch you have. We'll do it in the next release. We'll do it in. But the reality is that you ultimately need somebody high enough. Usually, the best person is the CEO to have enough. The problem with the CEO is he's supposed to be up here and not down here. But the best people, like Elon, are both places at once. They can understand those details, and then they can go and cut the decision and say, you guys don't even worry about it. We're doing it this way. And everybody, that's a great, for a certain set of engineers, that's a big fat piece of relief. They're off the hook and they can move towards the thousands of other things that are being pushed off because they were focused on this problem that didn't seem very achievable. And the good news is the worst scenario is when you have an organization where it's just like their management can't make any decisions. I mean, in a sense, that's where
Welcome to Volkswagen.
Welcome to legacy auto in general. Is that the problem? Isn't that people always say, well, they don't have good people. No, they have a lot of really good engineers. The problem is nobody is willing to stick their head out and make the organizational and necessary
or is even structurally capable of having that amount of influence.
Yeah, and that's why the closer it is to the top, the easier it is to make them, because you may have some VP over here who says, I want this to be true, but he's then got to negotiate with this VP to make it so. But if that person is, in charge of everything, then it's the benevolent dictatorship is a better model. But it requires that person to have all the facts or enough of the facts and have enough of the brains to make the right decision for the organization.
Very true. And that's one of the crazy things about, like, Elon is able to load in so much context about so much of his organization, so much of his mission, and, all the way, like you said, from the high level of, okay, what's our mission? What's our goal? What are we trying to achieve? All the way down to, I can't get this stupid, dry battery electrode cathode process to stop denting my rollers. Like, these little things are messing up. And okay, let's dig in and figure out, what are we going to do here? Are we going to keep soldiering ahead? Are we going to cut this project?
Right.
What's going to happen?
Yeah, and sometimes there's a myriad of things that end up happening, and one of the things that people see visually is commitments that then become decommits um, and get pushed off. And then your simple critics who either want to be critics and
He
also don't.
lied.
Yeah, you lied. I mean, it's such garbage. Look, great. People who achieve really great things in engineering are always optimists. That there is no second. I mean, in order to do SpaceX, in order to do Tesla, in order to believe that XAI could start now 2 years ago and have the best frontier model from nothing to this. And that whole process required the build out of that Memphis data center, which is a crazy, ungodly problem of many different trade-offs that were made. Um, you know, it takes a certain kind of person to be able to see that through, and you have to be very optimistic, which means that you are perceived by some as just liars because you're just optimistic beyond your capacity to deliver, or your capacity to deliver within a time frame that you set out. Like you also, you're as a senior leader in an organization, especially like Elon, the team, you put the team on a mission. So you kind of have to push them along, and what he says publicly can't be hidden from the team. So it's all one big pile of data at some point, right? The commits are so yeah, it's a really hard process. It's fun, it's hard, keeps you up at nights. And this is why, this is what we're living through with FSD, where I think one of the things that isn't said enough is about, say, a Tesla and an Elon, is that he is literally running us through how the sausage is made. I mean, he is exposing a process that in most companies are behind a marketing veneer, a wall that hides the dirty. I mean, all of the things we talked about in terms of, say building this iPhone 17 Pro and all the crazy, it's over here, all the crazy decisions that had to get made about how do you use this plateau, whatever they call it now, camera plateau, where do you stick? Oh, the antenna's now in here because we could, okay. All those crazy decisions that happen at Apple don't show up until stories after release. At Tesla, because Elon is inherently an engineer, that stuff you're living it. And if you um, don't know these disciplines and this isn't your line of work, and you hear this stuff, you just, without understanding it, you assume it's packed with fabrications, lies, deceptions, and you don't understand. It's like engineering 101, man. And it's happening at Apple. That's just not exposed. It's happening at Google. It's just not exposed. And Elon loves to expose it. I think that's who he is. And to me, there's great joy in that expression. In other people, it's not comforting.
100%. I think maybe
Yep.
that's a good place to wrap
Yeah.
for today. Um, yeah, I'm just really excited to see what version 14 has in store for us. I think we, or at least I felt similarly when they were talking about version 13 is coming, version 13 is coming. And we were just in this like long delayed pause of, basically no updates for hardware 3 cars or hardware 4 cars.
Right.
And it's like, okay, like I assume they're doing something. I assume like hopefully they didn't hit some crazy wall and now progress has just stopped. And then sure enough, it had of course not stopped at all. It had proceeded and they had just held back releasing what they were working on because they had a lot of work to do to make it ready for the public. And I think that that's going to be the case for version 14. I think if you just follow along the progress of the computing capacity that they have there at Tesla and how it's grown, it's pretty much impossible that they haven't made really, really good progress, and that they're going to have something magical to show us when they're ready to release that. But I am excited for it to finally download into customer vehicles and to be able to experience that for myself. And it's fun to get to think through, like you said, how the sausage is made and what is going to make this such a magical release for everyone.
Yeah, absolutely. I think that's the key is, if you want to follow Tesla, it's better to recognize how they are exposed as a company, without this big envelope of picture perfect marketing, and you get to see it, and you get really great engineering solutions to problems, and it makes people like me very excited. And that's why I follow them, because I get to understand the stuff and see it. And other people, I recognize that it's like they're just looking for the thing that drives the car perfectly, and they don't want to hear the daily blow by blow, and and they don't want to know something is delayed. They built a set of expectations that are just falsely grounded to begin with, and they now those expectations are the reality at which they're operating. And you have a company like Apple who just, what do we know about Apple? We know this: about this time next year, or a week or two earlier, they're going to release the iPhone 18, but we don't know anything else about that
Mm.
product. Right?
Except that it's going to be very similar to the iPhone 17, but with new colors.
Very likely. And then with any good luck, there's some newer model that, foldable, whatever, um, thinner, whatever. But yeah, new projects that come out of companies. I mean, one of the things that just to kind of complete this thought, and I think it's sort of interesting, is that, um, if you're an Apple, you're so you're so wrapped around the way Steve Jobs organized the company in this surprise and delight model, that you really, and given the size and success of Apple, you have to show up with a product that's awesome. Like like if you don't show up with awesome, uh, you know, you're laughed about, your sales flag. I mean, look at Vision OS, the Vision Pro and Vision OS. Really cool product if you ever put it on your head. But, price point is here, technology, and the companies like Tesla, while they deliver awesome, they they kind of yard it out. So we get to see that process. As we said, we get to see that process. And and I think that people like Elon think that there's this general forgiveness in the market for that. Yet people have been trained on, people have very, very high expectations of technology today. And they don't recognize the complexities involved in getting there. Um, and the funny problem that Apple has is that it's created an inverse for them inside, is an inverse to innovation. Normally, you would think, oh, this company was innovative. They're going to continue this approach. Oh, it's a leadership problem. And it sort of is. There isn't a Steve Jobs there. There is a Tim Cook, great guy, but not the same. But there's this other thing that's happened there, is all of middle to senior management are now risk averse, because you have to deliver awesome. So the only way to get out of delivering awesome is to not deliver a lot. You come back on that, and you would think, oh, delivering awesome requires extreme innovation, and but the opposite becomes true organizationally, to preserve your job, to keep, you know, and so it's one of the great reliefs that the team at Tesla has, is the guy that's willing to take the arrows in the back is named Elon Musk. And so now you're free to just work your butt off at any level in the organization. Yeah, you have a hard boss to report to, but you're given the license, I think, there to pursue the innovation and take the risk, knowing that failure is one of those potential options. And only by failure can you get into the next stage. And this is where Apple's kind of got stuck in a box right now, right? Um, So
Yeah, Tim Cook just doesn't have the wherewithal to, Steve Jobs was singular in his ability to facilitate and crack the whip on, no, like, this is not awesome. Go back, try it again, do something
yeah,
else, or we're doing something different. And so he was able to do that and manage the external public perception of the thing all at the same time.
yeah,
And then without him there, that's just not possible. And that's obviously not the way Elon does this. Tim Cook kind of does one side, Elon does the other side, and no one brings those two things together the way that Steve did.
yeah. Steve had unique. I mean, he a lot of little unique values there, but I mean, one piece of relief he had was he chose everything for Steve was about keeping secrets, even organizational walls. Um, the Mac division was over in a special building, and they weren't allowed to talk to other employees about their work product, so that it didn't leak. So that surprise, that moment of surprise, that moment of surprise and delight could manifest itself. But great relief on Steve as well, because he could run a whole team up a flagpole in some group that just hit a brick wall and failed, and nobody knew about it. You know, and we learned over the course of time that Apple was working on this car. They had Project Titan, and it was and there was a lot of leaks that came out, and under Steve Jobs' sort of uh, dictatorship, those leaks would not have occurred, and therefore very few people would know that Apple spent $10 billion on a project that didn't. I mean, that's a project where it's kind of hard to keep it contained, but
Mm-hmm.
some of the projects are a little bit easier to contain. um, like, it's hard for Elon, even if he was of this personality, it'd be very hard for him to hide SpaceX, because you got to fly rockets and in the atmosphere, and you can't just do
Mm-hmm.
that through simulation all the time. And to a certain extent, vehicle programs are like that too. The vehicles have to show themselves at some point on the road. Sometimes they're in camo, and you've seen, yeah, yeah.
Yep. All right. Well, I think
Alrighty.
we'll bring it to a close there. Thank you, Phil. Everyone, go and follow Phil on X at PBEISEL and check out his work. It's awesome. And we will catch you on the next time.